and thank you for joining us for our presentation on Web MapReduce for parallel computing at USI. Project was from our client, Dr. Srivastava, and under advisement from Dr. Gongjun Yan. And the motivation for our project is a National Science Foundation and IEEE TCPP initiative to get undergraduate parallel computing courses both here and across the world, including last semester's first project class on parallel computing taught by Dr. Srivastava, which our teammate John Bryan was in.
Thank you, Sam. So as Sam alluded to, last semester, for the first time ever, USI offered a special topics course, and it's called CS 499, Parallel Computing. And in this course, we learned all the various popular programming or parallel programming models. But what we found lacking, this was the first run, so we're kind of trying to tweak it and improve it for future iterations. What we found was that we were really limited in the type of environments that we could apply these models in. So we were limited to what the literature calls a pseudo-distributed environment, or kind of a single node or a single processor, maybe with multiple cores, or maybe even two discrete processors. And so going in future iterations of this course, we would like to expand the course material to include at least the fundamentals of distributed computing. So the kind of overall goal for our project was to provide our client, Dr. Srivastava, with the resources she needs to make that happen.
All right, so the reason that curriculum initiative was actually in place is because many schools lack the resources, the expertise, and the fundamental based learning material to actually bring a PDC course into fruition on their campus.
So the area that we'll be working in the background for this problem more generally is the massive amount of data that's created by running systems that can't be processed by a single machine because of the size of the data set, or because the amount of computation couldn't take place on a single machine in the amount of time that it needed to take place in. This affects many industries, including retail, manufacturing, genomics, and real-time credit card fraud detection, and logistics information for manufacturing, and so forth. MapReduce as a framework simplifies this work by separating out parts of the computation and running them separately in a framework that we have an example to describe to you. So in this example on the far left, you'll see there's a single box with several words in separate lines that repeat, and the goal here is ultimately to count how many instances of each word show up in that initial input. So splitting here is the equivalent of separating the data across separate nodes, and then mapping just takes each individual word and counts it as an instance and uses the word itself as a key for a shuffle where each word is shuffled together, and each instance is put into a set where the reduction can count how many instances occur in that individual set and then conglomerate to useful, humanly readable data at the very end.
All right, now that we've covered some background, I want to talk about kind of how we tackle this problem. So our approach can really be split into two parts, front end and back end, if you like to think of it that way. The front end, or the first piece of software, is Web MapReduce. It's a piece of software that was developed by another university, by another group of students, and abandoned sometime in 2012. It's exactly like it sounds. It's a very kind of simplistic web interface that connects to a Hadoop cluster to help manage and submit jobs to the cluster. So for this project, we wanted to kind of bring Web MapReduce back to life. Like we said, it was abandoned, and because it fits our use case perfectly. It really kind of lowers the barrier to entry for learning about this material, and allow students to just kind of jump in and get started, which is kind of the environment that we wanted. And then of course we have to actually build a distributed system to actually run these computations that the front end or Web MapReduce will plug into. And then we wanted to build out some example problem sets that students could use to kind of increase their understanding. And then so we developed this tool specifically for our client, Dr. Srivastava, and the CS 499 course here at USI. But we think a lot of other people could get use out of our work. So it was really important to this group to make it publicly available.
All right, so to actually get Web MapReduce functional, we had to make some adaptations to it. The first of which we did was add elapsed time, as you can see over there. Thanks, Sam. This is important because the whole point of exposing students to parallel computing is to show how much faster these applications run in parallel versus in serial. The second thing we did to add to the interface was add error messaging. This is obviously going to be important because some students, this is going to be the first time that they're programming in programming languages like Python, as well as the first time that they're running parallel applications. The third functionality we add was to view the dataset fields. This is going to be crucial for the students because for one of our examples, we have aggregated flight data for a couple different years. So if I had a problem and I said for them to pull out the specific year a flight took off, they're going to need to know exactly where that field is to pull that information out.
Thank you. So that is the front end. What does the back end or the actual distributed system look like? The architecture, we used Amazon Web Services and hosted it in the cloud. We used 11 Elastic Compute instances. So our cluster is set up with 1 master node and 10 worker nodes. That's just kind of distributed computing talk for, there's one server that's kind of the boss that is in charge of distributing work throughout the cluster, and there's 10 of them that actually perform the computations. In this case, either a map or a reduce function. And so in our implementation, if you use our images, it is kind of coupled. The WMR front end, the web MapReduce front end, is on the master image and is served from the master image. But that's just a cost-cutting thing because we're broke college students. If your company or if someone that you know wanted to use this, you could just as easily serve web MapReduce from someplace on-premise or another instance or anything else. There's a software stack down at the bottom if anyone's technical and is really interested in kind of what we use, but other than that.
All right, so the problem set that we implemented to support web MapReduce is built around data parallel problems. We chose to work with data parallel problems because they're very accessible, and they're also popular applications for illustrating the key strengths of the MapReduce programming model. Students can write fairly simple MapReduce programs to solve large data parallel problems. The problems that we implemented are from a wide variety of application areas. We have a few listed up there. And they were designed to operate on data sets of varying sizes in order to test the efficiency and versatility of web MapReduce. We then implemented and created solutions for over a dozen of these problems in order to verify that web MapReduce can actually solve a wide variety of data parallel problems effectively.
So as John stated, this project was originally abandoned in 2011 due to funding problems. So the Amazon machine images that they had uploaded to the Amazon Web Service Marketplace were no longer there. So we created our own images and we've uploaded those and made those publicly available for anyone to download. As well, the problem sets that Jake was talking about, we've aggregated all of those and we provide solutions in Python and Java to those and upload those to GitHub. And we are also currently in the process of publishing our user interface manual as well as our research paper.
So we're going to move into a live demonstration of web MapReduce in order to illustrate how it can be used to solve data parallel problems. All right, so when users start web MapReduce, they're going to be brought to the new job page. This page contains 4 input forms that users must fill out in order to create and submit MapReduce programs. The first form is the job info form. This is where you can specify kind of the characteristics and nature of your jobs. So you can create a name for your job that will be used to identify it on the interface. You can choose which programming language you would like your map and reduce functions to be executed in. We have provided support for Python, C++, Java, and C. The map tasks and reduce tasks allow you to designate which or how many nodes on the cluster are dedicated to either map function tasks or reduce function tasks. And the sorting here. There we go. The sorting allows you to specify the sorting criteria for your output itself. So you can either choose alphabetic or numeric sorting criteria. The second form is the input form. This is where you will choose how your program receives input, what data sets it's going to use. So you can choose from a few different data sets that we've already got uploaded to the interface. Alternatively, you could choose to specify a file path on the cluster that the data set's actually located on. You could upload a file, such as a CSV file, or you could manually type in your input. And this is really useful if you want like a really quick test scenario because it allows you to just write something up real quick and test to see if something works. And then the final 2 forms allow you to specify how and where you're going to get the map and reduce functions for your actual job. So you can either provide direct input for those and type them up here, and this allows you to use Web MapReduce's interface as kind of a small-scale isolated development environment, or you can choose to upload a program file that contains the programs themselves. So we've already have those here. So once you've got all of that specified, I gotta go back. There we go. All right, so once you have all that specified, you have three options. You can either choose to submit your job, in which case it'll just carry on like regular execution. You can submit it as a test job, which will allow you to see the intermediate output of your map function, and this is really useful for debugging and testing. And you can also click Save, and Save allows you to save your configurations that you've already set up. So if you do that, you'll see a little indication at the top saying configuration successfully saved. What does that mean? If you go over to the Save Configurations tab, you will see all this information that we just entered into the interface is saved here. And now if you hit New Job, it'll pull up everything, all your configurations, all of your settings. It'll all already be there so that you can jump straight into development. You don't have to worry about setting anything up. So if you hit Submit, you're going to be brought to the job summary page. This page, at the very top, there's two views that will allow you to monitor the progress of your map and reduce functions during execution. There's a progress bar that will slowly fill up. And then once those two functions are finished executing, you will either receive an error message if for some reason your program was submitted in error, or if it completed successfully, you will get an output that's formatted in the way that you specified in the reduce function. Since this was submitted correctly, we did get an output. And for this particular application, the data set is a poker hand data set. And the purpose of this particular program is to find the number of occurrences of any type of flush for each given suit within the data set. So, for example, here we've got the suit, which is hearts, straight flush, which is a type of flush that has occurred, and then a number signifying how many times that actually occurred within the data set. And then the final view at the bottom is the job info view, and this just contains like a generic summary of your job itself. It contains the name, whether or not it was submitted as a test, the identification number for the job on the Hadoop system, the output path, parallel execution time, which is a really useful metric for measuring the efficiency of your programs, and then also the code for your map and reduce functions. And finally, at the very bottom, if you hit Resubmit Job, after executing, it will bring you back to the new job page with all of your savings and configurations already there, so you can just begin development again. So we're going to move back to the presentation.
Conclusion. All right, so in conclusion, as we just demonstrated, this is currently up and running. Some future work that needs to be done on the cluster is scalability to deal with the influx of students using it. So our project's going to have an impact in a few different communities. First being the students. Obviously, they're going to get exposure to parallel computing for probably the first time and get this use this application to actually run some of their first programs. Also, the school is going to benefit from this because we are going to be passing this cluster on to them for further use, so they can use that to further develop our special topics course or actually try and get a PDC curriculum class added to the curriculum here at USI, as well as the local PDC community. As we've said, we've made all of this open source, so they're going to be able to download our images that you can see right there. It's on the Amazon Web Marketplace, and they're going to be able to set up their own cluster much easier than we did. They're going to have example problems for them to run through. They're going to have documentation on how to actually use the interface, and they're going to have a paper to read about what we've done. And also the local community around USI and Evansville will benefit because we're going to have students that are more versed in parallel programming, what's really becoming applicable in many different fields. And we'll open up for questions.